In the previous video, we looked at the dynamics of a simple pendulum from the work energy perspective. The only force doing work on the pendulum is that due to gravity, and since that weight force is conservative, we can derive a potential for it. And we get that the kinetic energy plus the potential energy adds up to a constant. Now let's look at another type of pendulum. For this one, the rigid rod is replaced by a spring. I call it the springy pendulum. Right away, we see that the dynamics are a bit more interesting. You will recall for the previous pendulum, it would never swing all the way over the top, at least not for the initial conditions we gave it. However, for this springy pendulum, it's not uncommon to see it go all the way up and make it over the top going clockwise. And then on the next pass, you see it doesn't quite get to the top. And then when it comes back around again, check it out, goes all the way over, right? Switched its own directions. This is the same initial condition, leads to all these different types of behaviors, including this behavior where it bounces up and down at the top like a pogo stick before it finally falls over the side. If we construct the free body diagram for the springy pendulum mass, we see it has a weight and it also has a spring force. And if you look at it, it looks remarkably similar to the free body diagram of the simple pendulum, right? The only difference is that whereas in the simple pendulum we had a rod force that could be either in compression or tension, in this case we have a spring force that could be in compression or tension. So let's start off doing the same thing we did with the simple pendulum. We'll take the kinetic energy, which is just 1/2 times the mass times the speed of the mass squared. That's this orange bar we see it here at the top. Notice that it's always positive. We see that the kinetic energy is largest when the mass is moving fastest. Sometimes when it gets to the top here, that kinetic energy almost goes to zero when the speed of the mass goes to zero. We can almost see it right there. It's almost zero. Then we'll take the potential due to gravity. That's the green bar we see up here at the top. Now when we defined our coordinates, a height of 0 corresponds to the location of the spring attachment point right here. So you'll see that the potential due to gravity is positive when the mass is above that attachment point. And you'll see it go down below the attachment point. There it is, below the attachment point, and the potential is negative, right? Positive for above, negative down below. Now, in the simple pendulum, we saw that this kinetic energy plus the potential due to gravity, those two things added up to a constant, right? That's what we had before. Now let's try it again. Let's add those two things together. And that's this red bar, and ooh, what do you see? It's not constant, is it? This red bar is fluctuating. The red bar, again, is just the sum of the kinetic and the gravitational potential. And we see that this is the sum of these two terms is not constant for my springy pendulum, right? So what's going on? What I want you to do is pause this video and think about it for a bit. Why are these two energies not adding up to something that's constant? Okay, and think about it deeply. In the case of the pendulum, the simple pendulum over here, the force from the rod did 0 work. Why is that? Well, it's because the mass moved along a perfectly circular arc, and this force from the rod was always perpendicular to that circular arc. It's always perpendicular to the path of the pendulum. Therefore, it could not do work due to that normality of the force in the path. However, this time in the springy pendulum, the spring can compress, right? The mass can move inward and outward. It can move in the direction. It can have a direction of motion that has a projection onto the spring force. And that spring force does do work now. Now here's another question for you. Does that spring force do positive work or does it do negative work? Stop the video again. Think about it. Don't come back until you have things figured out, all right? Give it some real thought. So you recall that the spring force, I'll call it the magnitude of the spring force, is proportional to how much the spring is compressed or stretched. So that's the delta there, the stretch or compression of the spring. And And K here is that spring constant. Now, springs have a natural length. That is, if there's no forces on the spring, it has a length that it just sits at naturally, right? I'm going to denote that natural length by L0, and I can draw a circle of radius L0 around the pivot or the attachment point for the spring. So whenever the spring is stretched out, in other words, whenever the spring is outside, or the pendulum here is, the pendulum mass is outside the circle, the spring is stretched, right? And whenever it's inside the circle, the spring is compressed. The spring be pushing outward, right? And you can see this spring sort of dances in and out of that circle there. So it's going between compression and tension and compression and tension. And it's doing so. The work is what? Sometimes the spring is pushing in the direction of motion. Sometimes it's pushing or pulling in the opposite direction of motion. So it's doing both positive work and negative work. Now, because the spring force is actually doing work, we find that the kinetic energy plus the potential energy of gravity, they don't add up to a constant anymore like they did with the regular pendulum, right? We got spring also contributing to the energy budget of this system. Now, a question you might ask is that spring force conservative? Yeah, is it conservative? We've already seen earlier in this class that a spring that pushes or pulls along one direction, that thing is conservative. And the way we show this mathematically is we define the displacement of the spring x, and then the spring force is just k times x in the minus I hat direction. Define a potential, which is 1/2 k times x squared, and then take the negative gradient. The negative gradient is just obtained by taking the first partial derivatives of the potential v with respect to x and y and put in the I hat and j hat directions. And that just gives you minus kx in the I. So here's the gradient of the potential, and there's the spring force. They're the same, so this thing is conservative. So the next thing to ask is whether this spring remains conservative if its endpoints are allowed to move around in the plane. Now, one can argue this thing with very elegant symmetry techniques, but we're going to do a brute force calculation here. All right, so the first thing we're going to do is define the spring force. I'll call it Fs. And Fs is going to be just k times the amount that the spring is stretched, right? Delta is the stretch. Now, of course, I can define the stretch in terms of the length of the string. I'll call that L. In that case, the length or the amount of stretch will be L minus L0, where L0 is the natural length. Of course, now I have to turn it into a vector. So let me define this angle theta. And the piece in the I hat direction is going to be minus cosine theta. And the piece in the j hat direction is going to be minus sine theta. And there's my force vector. So the next thing we have to do is define the spring potential. And for that spring that just moves in one direction, it's 1/2 k times the amount of stretch squared. But here, of course, the stretch is L minus L0. So we'll rewrite this potential energy as 1/2 k. Now I'll use the coordinates of the endpoint of the spring. We'll call those coordinates x and y. So my length is x squared plus y squared, square root. We subtract off the natural length of the spring, and there it is. To calculate the gradient, we're going to need a partial derivative of the potential with respect to x. So notice how x appears in this potential. First it's squared, and then it's square rooted, and then it's squared after that. So this calls for some heavy-duty chain rule. Now the result is this hot mess. The minus sign over here comes from the fact that we're taking the negative of the gradient. And then I got 1/2 k, corresponds to that 1/2 k there. But then I've got the stuff in the parentheses squared, right? Take the derivative of that, I get the 2 times the stuff in the parentheses. Now dive into those parentheses a little bit more. I got the square root, right? Take the derivative of square root, I get 1/2 times that stuff to the power minus 1/2, and that leaves me with x squared. Take the derivative of x squared, I get 2 times x. So I'll get rid of some 2's, right? That cleans things up a little bit. Now let's rewrite this. I got minus k, and this term x squared plus y squared square root, that's just L. So L minus L0, and then on the right-hand side I've got an x, and then to the power minus 1/2, that's just 1 over L. So let's just divide by L. Now the other partial derivative, this one with respect to y, it's pretty much the same thing because y appears in the potential the same way the x does. So here's what we get. So one of these terms has an x over L, the other one has a y over L. So let's make a triangle and do some observations. Notice that the x over L, that's cosine theta, and y over L, sine theta. All right, so now let's put together our gradients. I should say minus gradient of the potential. Notice that both terms have this minus KL minus L0 term in there. So let's bring that out. And then in the I hat component, we've got a cosine. In the j hat component, we've got a sine. And that's it. So what do we have? At the bottom, you'll notice we have minus gradients of a potential. And if you look at those terms and compare it to the spring force we have at the very top, what do you notice? They're exactly the same. So the spring force can be written as the gradient of a potential. And here, right here, here's the potential. It's our potential energy of the spring. In fact, it looks exactly like the potential energy of the spring moving in just one dimension. So we have a system here where all the forces acting on the system are doing work. And all those forces doing work on the system are conservative. So what does this mean? This means we have a conservative system. It means if we take the kinetic energy and take the potential due to gravity and add to it the potential due to the spring, those three things should add up to a constant. Right now we're only adding in the kinetic and potential due to gravity, but I can easily click over this next button to add in the potential. Hold on. Add in the potential due to the spring. There it is. We see when the springs get stretched or compressed, we see that potential of the spring get big. But those three things add up to a constant. That red bar, and that constant is constant as it can be. All right, I'll just let you watch this thing. It's sort of fun to watch. I'll be quiet.